Okay, if we look at this topic has been subdivided into some bullet points. And if I bifurcate that, I would suggest that bullet points from here to here actually talk about inorganic chemistry and the naming the compounds in inorganic chemistry. However, this one in specific goes for organic. If I don't say it like that, I will put it in a different way, that this is for ionic compounds and this is for covalent compounds. That'd be another good way to put it, that the compounds are divided into two categories and their names are slightly different when we talk about their rules, putting their names for ionic compounds as well as for covalent compounds, right? So what we are going to do, we are going to start with ionic first. We're going to practice some of their compounds, and then we'll move on to covalent, and we'll talk about the rules of covalent. Before I go with any kinds of those rules, let me tell you that giving a name to a compound is a way of classifying it, and the classification depends on many methods. However, this is the most common method the whole world adopts. And this kind of naming is important that we understand, and we have some rules for the entire word to follow so that the differences between different parts of the words doesn't come in the way of naming the compounds. Now, there are some names which are same for all of the word, and we don't come up with a system of naming them because this name exists even before we understood about the compounds or details. For example, water, H2O, we're not going to put it into any chemical names or use that one for the set purpose, or ammonia or methane. These are the common names that we use in the same way. We don't change the names chemically. However, for the rest of the compounds, for most of them will have the names, and we have a certain way of naming them. Let's go through that way. Let's go through point by point. First thing, if we talk about ionic compounds, and as you understand, ionic compound is a combination of a metal with a non-metal. So we need to name both the metal part and the non-metal part for an ionic compound. Now, if there is a metal in the compound, it is named first. Remember, the name of the metal would be written first. For example, we talk about NaCl all the time. This is one of the most basic examples of ionic compounds that we usually give. So the name starts with sodium. Now we do understand there is a metal and there is a non-metal in the component, but we always name the metal first. Why? This is one of the most basic rules of naming. Number two, where the metal can come from more than one, can form more than one ion, then that means the name has to be changed slightly. Now this specific point actually goes for transition element. Transition elements are the ones that are present in the center of the periodic table, and we usually color them blue for that purpose. Now, they can form multiple ions. By that I mean, they may lose 2 electrons and form a positive 2 ion, like here iron does. They may lose 3 electrons and form a positive 3 ion, like here Fe positive 3, and they may lose more or they may lose less. They can show variable oxidation states, which changes from element to element. Some show less, some show more. So iron can have a compound with this ion. It can have a compound with this ion, positive 3. Let's say if it forms a chloride with this or a chloride with this, they both will have different formulas. The first one will result in FeCl2, and the second one will result in FeCl3. Now, if we call them both by the same name, just because this one has iron and this one has chlorine, and both of them do the same thing, we'll end up having the same name for different compounds, which definitely contradicts. So in order to eradicate this kind of contradiction, we come up with a different kind of naming. What we do is that we write iron first, as per the first rule we just discussed. And in this name, we are going to write 2 ahead of it in brackets. In this name, we're going to write 3 ahead of it in bracket. So the oxidation state, the valency, is written in Latin numbers next to the name of the metal with parenthesis brackets. This is the rule. That's how we start their names. So one of them will become iron 2 chloride and one of them will become iron 3 chloride. Most of the transition elements showing variable states end up having names like this, and this kind of name makes it pretty easy for us to judge what kind of variable oxidation state it's showing in a specific compound. For example, as soon as you'll read the name iron 2 chloride, you'll understand iron was a +2 ion in that case. And as soon as you read the name of iron 3 chloride, you'll understand that it has a +3 ion. All right. So this kind of naming actually not just makes the naming easy for us, but also from the names, we can reckon what kind of ions have been used in their formula. So we generally say that names correlate or are coherent with the formulae and vice versa. Moving on, the third point is all about the negative ions, means the nonmetal. We haven't talked about nonmetal so far. We're going to do that in this point. Compounds containing only 2 elements have the names ending in IDE. Every nonmetal has its name changed. Chlorine ends at ione, but we convert it to IDE. Chlorine becomes chloride, bromine becomes bromide, nitrogen becomes nitride. So the names of negative ions actually change, nonmetals actually change. In order to keep you away with confusion, you would see that the table we discussed on page number 73, this is like 3 to 4 pages back. On the same page, we have the diagrams for the polyatomic ions. You would see every non-metallic ion had been named the same way, except one. Now, and that one is actually positive, that's why. So chlorine has been changed into chloride, bromine into bromide, iodine into iodide, oxygen into oxide, sulfur into sulfide, nitrogen into nitride, and hydrogen into hydride. So if they form a negative ion and they are non-metals and they do that by the gain of electron, and we're going to use them in names as the second part of the name because metal comes first, we're going to end them up in IDE. No matter how the name changes, nitrogen to nitride, sulfur to sulfide, oxygen to oxide, iodine to iodide. So the list goes on doing the same. And as it is already mentioned in this table, I think it's pretty easy to go through the table once, look at the ions, their charges, and their names, and you can keep referring to this table back and forth. Soon, using this table frequently will give you the idea how to name the ionic compounds. So it's pretty easy to come up with a few examples. Now, the only exception to this rule, in which we're not going to have 2 elements, we're going to have more, but the name would still end in IDE, is hydroxide ion. Now, hydroxide ions are actually this OH negative ion. When it combines, let's say it combines with sodium, this entire thing would become sodium hydroxide. All right. If you're going to name that sodium oxygen hydride, that's wrong. Polyatomic ions have their specific name. So I was saying that if we talk about hydroxide ion and if we make a compound out of it, let's say with sodium, it would be something like this. Now, in this case, let's write the name of the metal first, that is sodium. And if we don't use the word hydroxide and instead wind it up with oxygen hydride, that would be wrong. The name has to be sodium hydroxide, which means that the name of polyatomic ions, the entire negative ions, no matter they are made up of 2 atoms, 3 atoms, or even more, has to be the given name, as we discussed like 3 to 4 pages back. If you remember, we discussed OH negative as hydroxide, CO3 negative 2 as carbonate, SO4 negative 2 as sulfate, PO4 negative 3 as phosphate, HCO3 as hydrogen carbonate, and NO3 as nitrate. So the names are going to be the same. We just use the first one in here as an exception to the 2-element rule. Moving on to the next point, we'll use these carbonate, sulfate, phosphate, hydrogen carbonate, or nitrate. And in this case, compounds have the polyatomic ions. And the good part about polyatomic ions is that the names end with ATE, carbonate, phosphate, sulfate, nitrate. So it's pretty easy to come up with the names of polyatomic ions. And again, the only exception is hydroxide, in which the name ends in IDE. So that's the only exception. For the rest of them, this is the only exception, right? For the rest of them, the name ends in ATE, whether it's carbonate, sulfate, phosphate, hydrogen carbonate, nitrate, ethanoate, the list goes on. So for polyatomic ions, the name end in ATE. For two-element rule, the names end in IDE. This rule also goes for OH negative ions, the only polyatomic ion in which the name still ends in IDE because of the name hydroxide. And we now know about showing the oxidation state next to the name in brackets, and finally the name of the metal written first. So if that's how we keep these 4 simple rules with us, we can always easily name ionic compounds. Let's go for a practice. I'm going to stop sharing the book and let's do a whiteboard practice. For example, this is the compound. Can you tell me what would be the name?
Potassium chloride.
Potassium chloride, right. So I'm going to shorten up the name of the metal first in order to keep writing it with speed. Let's do one more.
Rubidium iodide.
Rubidium iodide, right. So you can always come up with a name using the methods or the points that we just discussed. What if I change it and use a polyatomic ion instead?
Aluminum sulfate.
Aluminum sulfate, very good. So what if I use a transition element with it too?
Iron 2 bromide.
Now, how come you came up with the number 2 with it? That's correct. That's not incorrect. But how can you come up with that?
Because of the 2 that's beside bromide, that goes for the iron valency.
Good. What if I use a different transition element? How about this one?
Copper 4 sulfate.
Okay. And yeah, this is a good thing that you can cross multiply this too, but that doesn't work every time. Sometimes the states are actually balanced out in such a way that there are no numbers at bottom, Cu2, SO4, 2, and then we can simply write it as CuSO4. So it won't be copper 4 sulfate, it would still be copper 2 sulfate. And how can we come up with this too? Remember, if you're handling a polyatomic ion and there are no numbers below, that must means that the polyatomic ion, the charge has been cancelled out or simplified. In that case, remember, if its charge is -2, the charge on the opposite ion must be +2, and that too should be mentioned in the name. That's how it works. Right? So sometimes,
Okay,
yeah,
sir.
you can cross multiply, reverse cross multiply these numbers like you did with iron 2 bromide. Perfect. I like that. And in cases when these numbers are not written or these numbers have been used up in process of simplification, you need to come up with the numbers still that they might have been used in the process of simplification. So always keep an option open for simplification. And whenever you need to reverse work that out, you should and you can, so that you can come up with the correct number, right? For example, let's not go with that. Now PO4 is phosphate ion, CO is cobalt. This one works just like this one, copper 2 sulfate.
So cobalt phosphate? Or
It would be cobalt, and it would be 3. Why 3? Because this is -3. If phosphate is -3, this must be +3 in order to balance that out. So it's cobalt 3 phosphate. Clear enough? That's what I was trying to explain, that if this number has not been used or cross-multiplied, that means numbers have been balanced out in the process of simplification, which means the numbers still exist and we need to write it as a part of the name. Do you get the point?
yes, sir.
Good. I hope that clears it up. Now let's move back to the book. I'm going to stop sharing the whiteboard and share the book screen again. Let me know when you're able to see my screen.
Yes, sir.
All right. So we're done with the first 4 points that pertain to ionic bonding and ionic compounds. So now you know how to name the ionic compounds, whether it consists of just 2 elements or may it consist more. So let's come to talk about the covalent compounds. Covalent compounds are named somewhat differently, and I would rather say with a simplification. So the names of the compounds actually use the prefixes, and prefixes tell you the number of that particular atom in a molecule. If there are 2 elements forming a compound, the name would be pretty easy. However, for 3 elements, it would be a little different. Let's talk about 2 because the names of 2 elements are a part of your course. 3 are not discussed here, so we're not going to discuss that. That's beyond the requirements of your syllabus. However, some names are included into your syllabus with 3 nonmetals or 3 element-based covalent compounds, but their names are written along with them in the book, and you simply go with the memorization rule for them. You don't learn their complete naming. So we go as our syllabus document instructs us to. For that instruction, we're going to start with the covalent compound naming if they consist of 2 elements, right? Numbering must be written over here, and as it's not written as a part of the book, so we are going to write it separately. We're going to use the name or prefix mono when the counting is 1, di when the counting is 2, tri when the number of atoms are 3, tetra when the number of atoms are 4, penta when the number of atoms are 5, and finally hexa if the number of atoms are 6. So these are the prefixes commonly used in the naming. If the number of atoms are 1, you use the prefix mono, then 2 for di, 3 for tri, 4 for tetra, 5 for penta, 6 for hexa, so on and so forth. If you remember the numbering in this way, it should be easy. Then we again have a couple of rules. If the first element has just 1 atom, you never use the word mono with it. You simply name the atom. And for the second atom, we just name it like we did back in ionic compounds. The name ends in IDE, but this time we use the prefix, whether it's a single atom or more than 1 atoms, right? Okay, just give me a second. I need to take an important. And I was telling you that if there are 2 elements and the first one has 1 atom, we don't need to write the prefix mono. But whatever number of atoms are there for the second atom, we need to write them along with the IDE suffix added to it. So the name would be carbon, as the first atom is carbon, and then it would be mono, as there is only 1 atom of oxygen, and oxide, as oxygen is named as oxide. That's how we come up with the name. Let's go for a few more numbers, a few more names for practice. I'm going to stop sharing the book and I'm going to share a white screen page to get started with that. So let's practice a few covalent compounds. All right. For example, let's write the numbers and the prefixes over here. So it's not a problem for you to answer me. 1 for mono, di is for 2, tri is for 3, tetra is for 4, 5 is penta, and finally 6 is hexa. We're doing 5 and 6 just to be on the safe side. Usually the compounds that we see or we have seen in the past papers for 10 years come up to 4 atoms. There hardly have been a couple of names with 5 atoms. So this one would become carbon monoxide. Remember, we only write the name of the first element without the prefix if there is one atom. If there are more than one atoms, we use the prefix for the first atom as well as for the second one. For example, this one would become CO2 would be. Can you hear
Carbon
me?
dioxide.
Yeah, carbon dioxide. Let's try this one. What do you think the name would be?
Dicarbon trioxide.
Right, very good. Dicarbon trioxide. Now this time we started the name off of a prefix because the number of atoms of the first element weren't just one. There were more than one. So it would become dicarbon trioxide. Let's try this one. N is nitrogen. Can you come up with a name? Okay, let me help you with this one.
Sir, I'm unable to see your screen.
You're unable to see my screen?
Yes, sir. Can you share it again?
All right. I thought that would have worked, but let me do it again. How about now?
Yes, sir. Now I can see it.
All right. I think that was the problem. Okay, so let's try with this one. How about this one?
Nitrogen dioxide.
Simple and easy. Nitrogen dioxide. Let's go with some bigger numbers. What about this one?
Dinitrogen trioxide.
Good. What about this one?
Dinitrogen pentoxide.
Pentoxide. Very good. So you'll see that even if I change the numbers, now you got a hang of it, so you can always come up with the correct name. Let's try it with a different element. Like this one.
Sulfur dioxide.
Sulfur dioxide, very good. How about this one?
Sulfur trioxide.
Sulfur trioxide. So now you got a hang of it and you now know how to name them, right?
Yes, sir.
Good. So I'm going to save it up and stop sharing and we'll get back to the book. If the book is not shared in front of you, let me know. Every time if we have a screen sharing issue, let me know so that we can stay on the same page.
Okay, sir. I can see it now.
All right, good. Now, as soon as we're done with all the bullet points, you would note a few important things written over here. So let's come to that. The names for important mineral acids are systematic, but they are just learned at this stage. For example, sulfuric acid is H2SO4, hydrochloric acid is HCl, nitric acid is HNO3. So you're simply supposed to memorize the names. And let me tell you, the number of times we're going to use the acids in the acid bases and salts chapter, which is chapter number 5, by the way, in this book, you will automatically memorize them. You won't have to go through an effort to cram them up. But they are systematic, and what are the systematics? We'll learn that in chapter 5, not here. So it was just the piece of information we needed to go with. There are a couple of names more. Oxidizing agents consist polyatomic negative ions. They include metal atoms as well as oxygen atoms. And we need to memorize their modern names. For example, potassium manganate 7 is KMnO4, and potassium dichromate 6 is K2Cr2O7. Now, these are the ones you're supposed to memorize the names as well as the formulas. You're not going to go with how we name them right now. No, none of the rules either, but you're simply going to memorize the formulas and the names. That's about it for the nomenclature part. If you have any questions from the nomenclature part, let me know. Thank you for that. I literally forgot about it. Okay, so
No
we were
problem,
talking
sir.
about metal crystals, and let me revise a little bit quickly, real quick. We were talking about metal crystals and the bonding diagram we did previously, which is pretty similar to that one. Metal cations in the center packed in tight layers, and electrons moving around it in like a sea of mobile or delocalized electrons can explain all the properties of metals. For example, metals are solids and have a high density that comes from the tight packing. The high melting and boiling point also are due to the tight packing. Now, there are very strong forces of attraction in the metal, which also results in their high density, high melting, and boiling points. When we talk about other properties of metals, I hope you remember that yesterday we cleared about the electrical conductivity due to the presence of these delocalized electrons, and these charged particles can carry the current. And I explained thermal or heat conductivity because of the vibrations of these metal cations. Not just that, if you're supposed to explain the malleability or the ductility of the components, we can explain them by a few simple diagrams that, there you go. This figure 3.34 can easily explain you the concept of malleability or ductility. The metal cations are present in the form of layers. Apply any force on them and the layers can slip over one another. Because of this property of slipping of layers, they are malleable and can be converted into sheets, and they are ductile and can be converted or stretched or pulled into wires. So this property of slipping of layers can easily explain both the malleability as well as the ductility. I hope that explains how and why we use metals in such a way, right? Moving
Yes,
next,
sir.
the metals can be converted into alloys. Alloys are simply the mixtures of metals and sometimes even non-metals to get specific properties imparted to them. Alloys are better explained on page number 81 in a table. When we talk about this table, I tend to ask my students that do not go with these percentages. You're not supposed to memorize them. Memorizing the name of an alloy along with which elements it's made up of and what particular property does it have is good enough for the exams. For example, brass is an alloy of copper and zinc. It's harder than pure copper and it has a gold color. That's why it has been so attractive for humans as an alloy. Now, adding zinc to copper actually gives us hardness. How does that happen? We're going to explain it in the diagram below, but a little later, let's go with some more alloys before we explain this diagram. The next up in the list is bronze. Bronze is actually a combination of copper with a little amount of tin. That tin increases the hardness of pure copper, and that's why we have been using bronze as of a major used alloy lately. I hope you remember that the medals we usually give away in our Olympic championships are gold, silver, and for the third position, we usually give away bronze. That's like all around the world. Next, we have on the list is mild steel, which is stronger and harder than pure iron. This is because of the very small addition of carbon atoms to iron, right? So keep in note that which element we're adding and what property we're getting out of it. For stainless steel, the name stainless comes from the fact that the steel cannot be rusted and thus cannot have a stain. It shines and it has a very pure and attractive finish. That shines come from, or the not rusting property comes from chromium. Keep that in mind. Mark it on the book if you want to. That chromium actually gives it the property of not rusting, and nickel is capable of giving it the hardness and strength we require out of stainless steel. Next up on the list is solder. Solder is a combination of equal amount of tin and lead, and it has lower melting point than either tin or lead, which is actually beneficial for us when we are dealing with electrical circuits. So when we talk about alloys, the elements we mix and the properties we get is good enough for us. We don't need to go with the percentages in IGCSE. Now, as we have been saying that metal becomes harder and stronger after the addition of another metal or non-metal to it, what happens can be seen in this diagram. This diagram has three parts. Let's look at the A part first. It's a pure metal. It has all the ions of the same size. So whenever a force is applied, the layers would easily slip over one another. That's what actually happens in the B part of the diagram. But if you have an alloy, the alloy must have at least two different metals or a metal with a non-metal, or maybe more than two. In that case, the size of the particles will not be the same. Remember, there is bound to be a metal which has greater atoms and another which has smaller ones or bigger ones in comparison. What happens when we apply force over here is that the bigger atoms tend not to move, disturbing the slipperiness of the entire layer. Now, this means that the structure is going to be harder than before and stronger than before. What isn't mentioned in the book, and you need to understand, is that this is actually a compromise on malleability. Remember, harder structures are difficult in terms of their layers to move or slip over one another. So they are a little bit difficult to mold or to give shapes to, right? So yeah, they definitely become harder and stronger, but we need a compromise on some other property, maybe malleability, maybe ductility, maybe some other property. But it's not that we are interested in malleability or ductility at that time. We are sometimes interested more in hardness or strength, or maybe the not trusting capability, or maybe a lower or a higher melting point. So it actually really depends upon the use of humans, how they're going to use it. So we change the properties as per our need. So we keep adding or removing metals into different metals, forming alloys and using them to our advantage. Are we clear about this one?
Yes, sir.
This finishes the metallic crystals for us. Next on the list are ionic crystals. We have already discussed the properties of ionic crystals. However, those properties are discussed again over here, keeping in mind the entire structure of the ionic lattice. Now, if you take a look at the ionic lattice, it actually consists alternate positions of positive and negative ions. In an ionic lattice, the nearest neighbor of an ion is always of the opposite charge. Pick this one up. Next one is negative on all ends, no matter which end you look at. So when we talk about sodium chloride, every sodium ion is surrounded by 6 chloride ions. Sometimes the student wonder that how come it's surrounded by 6 and not by 4. Let me explain that. If one sodium ion is in center, A chloride ion will be at front, a chloride ion will be at back, a chloride ion will be at its left, a chloride ion will be at its right, a chloride ion will be at its top, a chloride ion will be at its bottom. And it actually works in the same way as we does in mathematics in terms of axis. This is x-axis, this is y-axis, and this is finally third dimension or z-axis. So there are chloride ions present in axis and the anti-axis in all sides. So hence, every positive ion is surrounded by 6 negative ions, or every negative ion is surrounded by 6 positive ions. And that's how the charges balance, because we have equal number of positive and negative ions to cancel out the effect of the charges, and the formula stays as a neutral one, NaCl. This doesn't just happen in NaCl, this happens in every single ionic compound. The charges balance with one another, and that we have studied from the structure, the formulation specifically. I hope you remember that we canceled out or balanced out the charges in order to get the formula of an ionic compound. Now, the actual arrangement of ions actually depends upon the number of ions involved in a formula. However, we're not going to do that thing. The only important thing is that they're all electrically neutral, as I just explained. Electrically neutral means the charges have balanced one another. The next property at hand is the brittlety. Ionic crystals are hard and much more brittle. Brittle means we cannot shape them with force. Instead, whenever you apply force to shape them up, they would break instead of getting molded or getting shaped. This is actually the result of their structure in layers. Now, take a look at this figure 3.40. It would give you a very good idea how that happens. Now, they are present in alternative arrangement. And if you'd like to apply force at certain layers so that the layers might slip over one another, they do slip. But when they slip, actually, all the repulsive forces get into play because the charges, similar charges, come in front of one another. Positive faces positive, negative faces negative. These repulsions cause the crystal to fracture, and the entire compound, instead of changing its shape, breaks. We call it brittle, right? Now, this kind of destruction is also brought about by water. Ionic compounds dissolve in water because water is able to interact with them. Water can break them apart. Water can break the entire lattices. How? Water takes away the positive ions as well as the negative ions. Now, this diagram confirms that the bigger ones, or the ones drawn in cream color, are actually chloride ions. The one drawn in the smaller size are actually sodium Na positive ions. Water is capable of surrounding their ions ion by ion separately. It takes time, but it is capable of breaking the entire lattice up and surrounding every ion separately. Take a look. The sodium ions are surrounded by water molecules, and here the chloride ions are surrounded by water molecules. So when water tries to break the lattice apart ion by ion, it slowly takes some time, and the ionic compound actually dissolves in water and disappears. That's what actually happens when you physically observe it. Take a glass full of water, take a spoonful of salt, throw the salt into the glass. You would see that the salt would settle at the bottom of the glass. But once you start stirring, slowly the salt dissolves and at the same time disappears. That disappears because water is capable of breaking the entire lattice separately into positive and negative ions and surrounding them up. This process in common language is known as dissolving. That's how water is capable of dissolving ionic compounds, because it is capable of breaking the entire lattice up into positive and negative ions separately. But for some ionic compounds, water does not have the capability to do that. What we simply say is that those compounds are insoluble in water. So now you'll simply understand
The salts that are soluble in water, it means water has the capability of breaking their lattices into positive and negative ions separately. And if a salt is insoluble in water, it's pretty simple that water does not have the strength to break them apart into their positive and negative ions. Are we good with dissolving
Yes, sir.
solubility? Good. The last point we have is that when water is capable of breaking the lattice apart and dissolving the ions, converting them into positive and negative ions separately, the ions can flow along with water molecules. When the ions can flow and are able to move, they can carry the electric current, and hence salt becomes a conductor when dissolved in water. The same is true when it is melted, because as soon as we melt a salt, we break the entire lattice up into positive and negative ions, making them free to move. And when they are free to move in a molten or a liquid state, they're able to carry the current. Remember, current is always carried by charged particles. Any compound is made up of charged particles, positively and negatively charged particles. But if they're free to move, the ionic compound will become a conductor. If they are not free to move, the ionic compound will become an insulator. So the ionic compound is an insulator when in solid form, because the ions are not able to move, but it is a conductor when it is either in molten form, because that's when it is a liquid and they are free to move, or when it's in aqueous solution form, right? So these are the two conductor forms, and molten is also the conductor form. Insulator is when it's in solid form. Are we good with this one too?
Yes, sir.
All right, great. Up next is the macromolecules, the topic we have been keeping pending for a lot of time, the giant molecular crystals and the simpler molecular compounds. So we have just two small topics, we can say hardly 2 pages left out of chapter number 3, but I'm not going to do them today. I'm hopefully going to cover them tomorrow, if that's fine with you.